Or- There we go. Good evening, everybody. My name is Terry Eichel, and I work with the Interreligious Eco-Justice Network, a faith-based environmental group in Connecticut, and we work with religious communities on environmental issues. Thank you so much for taking the time to join us for the many problems of microplastics. I would like to open first with our IREJN's land acknowledgement statement. We acknowledge that Connecticut, Algonquin for land on the Tidal River, is the traditional home of Mohegans, Pequots, and many other tribes. We are grateful for our Native people's care for their home and will strive to preserve it for the next 7 generations. You know, Mary Evelyn Tucker is one of my favorite people, and she once gave a talk where she said, "The Earth is facing 3 environmental crises at the same time: climate change, toxic pollution, and biodiversity loss." And that has always really resonated with me. And at IREJN, we really strive to educate and motivate people of faith and religious communities to take action on these 3 issues from a variety of perspectives. Today, we are joined by 2 young researchers from Washington, D.C., Joseph Barnes and Alyssa Davey, for a presentation on microplastics, what they are, how they are interacting with the environment, and what we can do about them. After their presentation, we'll have a moderated question and answer session, and you can put your questions in the chat or in the Q&A. So actually, let me share my screen again so that I can get you to their bio. There we go. So Elisa is a physical scientist in the Office of Research and Development at the US EPA. She began her microplastics research at American University in the fall of 2020. Her thesis project focused on microplastic and PAH pollution in sediments of the Anacostia River in Washington, D.C. Elisa's microplastic expertise lies in polymer chemistry, water pollution, and sedimentology. Her thesis research was published in 2023 in the journal Water, Air, and Soil Pollution. Elisa earned a BS in biology and marine science from the College of William and Mary in 2014 and earned her MS in environmental science in 2022. She enjoys hiking, crocheting, and making new friends at the dog park with her puppy Pearl. Joseph Barnes received his Master's of Environmental Science from American University in May 2023, where he studied how biological and physical conditions of the Potomac River affected the distribution of microplastics in the water column. During his graduate studies, Joe also conducted literature reviews on microplastics studies, policies, and the market interactions of these pollutants. Joe has appeared on NBC4 News, the How to Protect the Ocean podcast, and spoken about his research at various conferences. Joe's environmental science career has extended to aquaculture, wastewater testing, oyster, and climate change research. Sorry. Oh, I am so sorry. Joe, my screen sharing just went away from me. Joe is also our former board of director for the Interreligious Eco-Justice Network. He served as our secretary for many years, and we love him. So he's awesome. Joe, I apologize. My PowerPoint got away from me. But without any further ado, I would like to bring Joe and Elisa on. Thank you so much. And as I said before, guys, we've got a Q&A. I guess just Q&A, actually. So put your questions in the question and answer, and we'll get to them after the presentation.
Thank you so much, Terry. Not a problem at all about the screen sharing. I'm going to share my screen now and then turn it into a presentation. Here we go. Awesome. Thank you again, everyone, for coming out tonight. I'm very excited to talk about the research that I and Elisa have done on microplastics and just talk about the many problems that they pose in our world, and also some solutions and how we can follow up and address the problems. So we're going to run through a little bit of background about ourselves. Terry did a great job covering that. Thank you again. We'll talk about the research that we did. So I did biological and physical interactions of the Potomac River on microplastics. Elisa will speak about her chemical analysis. We'll talk about some risk assessments and policies, both in action and proposed, and summarize it from there and go into a Q&A. So thank you again. Let me change this. There we go. So I recently got my master's of environmental science from American University, where I studied microplastics. And more specifically, I was looking at how different algal and microinvertebrate species affected the distribution of microplastics throughout the water column. And I'm going to talk a lot about that. But my experience isn't just limited to microplastics, although I am obsessed with them. But I also did work on global seafood trade and did case studies related to different geopolitical events and how that affected seafood trade. And I have a lot of experience teaching environmental science. And so I love doing things like this and just talking to different audiences about various environmental science topics. But what got me into microplastics at first? Well, I'm sure, like many people, it was this viral video of the turtle where a researcher found a turtle in the ocean, pulled it up under the boat, and found a plastic straw stuck in the turtle's nose. I don't know how it happened, but it just shows how prevalent plastic is. It was actually a friend of mine in undergrad who was in a basic ecology course and doing a project on plastics that brought this to my attention. And then after that, I started to realize just how prevalent plastic was, where I was using it in my everyday life. And after my undergraduate, for a few years, I went into different elementary school classes and as a guest scientist lecturer and talked about climate change and just a way to supplement their environmental science unit. I ended up using plastics as a proxy to talk about all the ways that humans interact with the environment because it covers the biosphere and the hydrosphere and the atmosphere and all the ecological spheres. And because plastic is found in all of those. I started to realize, like, I started to get imposter syndrome, honestly, and thinking, why can I speak about this? I've never actually researched them. I've never like been in a plastics lab. And so I thought, well, I'm going to change that. And I wanted a master's anyway for higher education. So I found a lab at American University and studied microplastics. I'll pass it over to you, Lisa.
Hello. So my story is a little bit similar to Joe's, but I got my master's in environmental science from American University. So with my thesis research, I looked at microplastics in sediments as well as polycyclic aromatic hydrocarbons, which are chemicals that are a result of the combustion of fossil fuels. And then I also focused on polymer chemistry. So I analyzed the microplastics that I took out of the sediments to find out what type of plastic they were, to hopefully find the source of the plastic, as well as identify any chemicals that were associated with the microplastics that may be attached to the microplastic or were added into the plastic when it was produced. So after I graduated, I was very fortunate enough to get a fellowship with the EPA. I always had my eyes on the EPA. That was my goal when I went into grad school. I wanted to do research and then, go to the EPA to do more public service and engage with environmental science in that way. So I was in the Office of Water and I was on the biosolids team. And my project mostly focused on microplastics and biosolids, and then how we could apply that research with risk assessment. And I put the smiley face there because I will talk more about that tonight. And then a couple months ago, I was brought on as a permanent federal employee in the Office of Research and Development. And I work in extramural research. So that is facilitating research, environmental research in many different topics. So the EPA actually, most of the EPA's funding goes elsewhere. That's either with partnerships with states, communities, and tribes, or with extramural research. So we fund research that helps people. And then there's also an environmental justice component to that, which I really enjoy. So we make sure that underserved communities are engaging in research and the communities are being researched, so we can make sure that everybody has equitable environmental outcomes. So I have to have a little disclaimer, because I'm here on my own time. I'm not representing the EPA tonight. So this is my federal employee disclaimer. So this presentation contains the personal views of myself, and it's not official representation of the EPA's policies, practices, and viewpoints.
So before we get into the nitty-gritty part of everything we're going to talk about tonight, I want to take a few seconds to put in the chat any plastic object that you've used today. And you can think about where you were when you used it, what color this thing was. Did you throw it away afterwards? Was it just a single-use item? What was the shape? And I'm gonna open the chat if you feel comfortable, and we can kind of talk about where plastic factors into our everyday life. Right now, I'm looking around my desk and I see a lot of plastic wires. For one, I have an HDMI cord that has an adapter to plug into an HDMI into my computer. My computer itself is somewhat plastic. I have a reusable set of cutlery, but that's also plastic, and I washed that today, so it's on the drying rack out in the kitchen. But I was putting away Christmas decorations recently, and a lot of that was plastic. Like putting the plastic Christmas tree away, there's still needles that fall off, and that turns into microplastics. But we get the idea. There are a lot of ways that we see plastic. So what are microplastics? Let's start at the very beginning. They're any piece of plastic less than 5 millimeters. And that's about the size of a pencil tip eraser or a grain of sand. They are very small. There's a couple ways that they end up in the environment. There are primary microplastics, and those are things that are intentionally created to be that small. So some examples are clothing fibers. These are just small pieces of like nylon or whatever poly blend your clothes are made out of. Or a good example I like to give are nurdles. And nurdles are these small plastic spheres that are melted down during their cycling process from other plastics. And then those nurdles are a specific type of spherical plastic that are then remelted and formed into another type of plastic. That's how things get recycled. But the thing with nurdles is that if you just Google it, if you just search for nurdles, you're going to read about the spills. They are so frequent. But we also get secondary microplastics, and those are any plastics that break off of larger pieces of plastic. For example, a water bottle just sitting out in the world. That's going to be exposed to oxygen and UV rays from the sunlight and just stress and abrasion from being blown around. All of that activity breaks down the water bottle, breaks down any piece of plastic. But because plastic isn't naturally found in the environment, it only breaks down into smaller and smaller pieces of plastic. There's no biological component of it to break down into. And microplastics are so widespread that they are found across all environments studied.
All right, now we're going into my favorite part about microplastics, is the kind of the chemistry behind microplastics. I know some of your eyes may glaze over. This used to be me, but I'll try to give you the lowdown. So what is plastic? So plastic is an organic compound, not organic in produce, but organic as in carbon based. So plastic has that carbon backbone. So you can see in the polyethylene, the polystyrene, and the polyethylene terephthalate, you can see those strings of carbon. So that is the core of plastic. And then we have different functional groups as well. So you can see with the polystyrene, the functional groups are those benzene rings that are attached to the carbons. So that is what makes the plastic different. And plastic is composed of monomers. So if you look at the bottom with polyethylene, you have those ethylene monomers. And then in the production of plastic, a chemical catalyst is added, and then that that induces polymerization, which makes plastic. So it induces that chain of carbons to form. So there are also naturally occurring polymers. We are most aware of man-made polymers, but beeswax, any type of wax, is also a polymer. And then plastic can be made out of oil from fossil fuels, but it can also be made out of vegetable oil and plant-based and natural sources. But plastic is plastic. So the environmental footprint of fossil fuel-based plastics is different, but in the end, they all kind of behave very similarly in the way that they're formed. So plastic is pretty diverse, especially with the chemical composition. So if you think, you guys have in the Q&A have added some of the plastic you've used today and you've seen around. And if you think about all of the plastic you've encountered, there are a lot of different types of plastic and different functions that they serve. So you can have a more rigid plastic that holds your takeout, or you can have a plastic tube that's really bendy for your fish tank. So there are additives that are added with in the production process to give plastic different qualities. So those can include flame retardants, plasticizers that make them more flexible and bendy, colorants, fillers to kind of bulk up the plastic, and then stabilizers. Sometimes stabilizers are to make it more rigid, or to just add some bulk in there, or to stabilize the polymerization process. So you'll see that I added these recycling numbers. So I hope we're all familiar with recycling numbers, maybe not necessarily why we have different numbers on the bottom of plastic, but that denotes the type of plastic, the type of polymer that a certain container that you want to recycle is made out of. So I want to highlight number 7 because a lot of places don't take number 7. And something that's notorious for being a number 7 is laundry detergent bottles. But the reason why it says other is because different types of polymers can be added to each other to create copolymers, and so plastic is very chemically complex, and we'll get into the implications of that. Next slide. So with all of that, it's pretty clear that microplastics are very diverse. So especially in morphology, we have a wide range with between 1 micron and 5,000 microns, or 0 and 5 millimeters, which is oversimplified, but there's a huge range of sizes that we can find these in. Some of these we can see with our naked eye, some of them we can't, most of them we can't. And then we have different shapes. So we have fibers, spheres, and fragments, films. We use a lot of plastic films, and those break down into smaller pieces. And then we have different colors. And sometimes the color can kind of give us a hint as to where the plastics came from. And then because of the small size of microplastics, there is a high surface area to volume ratio. So that lends itself into, there's a lot of surface area for things to attach, for the microplastics to interact with their environment. And then within the diversity of chemical composition, this can lead to a difference in density. So different microplastics can behave differently in different solvents, or like especially in water. Some microplastics will float and travel with water. A lot of microplastics will sink directly into sediments and stay there for a long time and interact with the sediments that way. And then they also have different degradation rates. So they break down at different rates. They release different chemicals at different rates. And then they can also interact with contaminants. So Microplastics are hydrophobic, or they're scared of water. So any lipid-based or any fat-based contaminant is really attracted to the surface of microplastic. So that can include DDT, PAHs, BPA, phthalates. BPA and phthalates we know are endocrine disruptors, so those aren't fun to have interact with something we see so much of.
Yeah, and I'm sure that for those of us in Connecticut, we may remember the firefighting foam spill in the Farmington River a few years back, and those flame retardants are plasticizers, as Elisa said. So this is just a very nuanced and widespread pollutant. And because they're so varied, because they are found everywhere, there's no known large-scale removal method. Once microplastics are in the environment, they're kind of there. We can track and monitor where they may end up, but there's no great way to remove all of them at once. And so as all these microplastics are just floating around their environment or being buried in the sediment or blowing around in the wind, there's a lot of interactions that happen when they come across the flora and fauna in those environments. Microplastics, plastics in general, can be inhaled. They're in the air. They're being inhaled. They can be ingested, as we see a lot with whales, for example. Larger whales' autopsies frequently show just a stomach full of plastic bags, or turtles eating plastic bags, mistaking it for jellyfish. In some cases, with plastic food takeout containers, microplastics are leaching out into our food there. They can have entanglement interactions, and for larger pieces of plastic, that can be physically entangling other animals. Things like fishing nets, ghost gear, abandoned fishing nets will wrap around whales, or fishing line, things like that will wrap around animals. In smaller cases, that can revert to things like seagrasses or corals actually entangling the microplastics and stopping them in their tracks. Absorption, I wanted to put this word here more in the sense of them settling out in the environment. So being deposited into sediment, or just being added as a polymer into another type of plastic and then leaching out into another type, like like the food in a plastic takeout container. And there's adsorption techniques. So that is when something just attaches and gloms on to that surface area of the microplastic. The research that I looked at these flora and fauna interactions, but at a micro scale because of microplastics. And that was in biofilms. And a biofilm, as we'll see on the next few slides, that is an assembly of microorganisms and microalgae or micro seagrass type species. These are things that settle out of the water onto a surface and just grow, just live their lives. But because plastic is so widespread, it's actually given way to a new type of ecology. So like I said before, there's the hydrosphere that deals with anything water related, the atmosphere, anything air related. There is now the plastosphere, because there's so many things living on plastic. And one of those things are bacterial and algal transport mechanisms. This means that bacterial species and some algae can attach themselves to that surface of microplastic and be carried around the environment. They can be carried across oceans with the wave action or blown around in the wind. And this is really important to know about because all of our watersheds are connected, whether it be underground aquifers or through stormwater runoff and rain running over a sidewalk or a concrete path. So we'll get into this a little bit further. Right over here, actually, let me go back to that picture. That aluminum disc that I'm scraping off of, that's me getting a sample of those biofilms. So even the biofilms are pretty small. And looking at it under a microscope, this is one of those seagrasses that I was talking about. If this was in the water, it would be kind of sticking upright and flowing a little bit. It is dried out and on a microscope slide, so it's flat there. But in another dried out sample of these biofilms, so this is mostly just some sort of sediment, but right there in the middle is a microfiber, this clear, translucent, shiny fiber, microplastic. And then another example of a dried out biofilm that I was looking at, we found this little amphipod. That is just a small little crustacean creature that can settle into a biofilm, scurry around, eat some of the algae. Very cute. Unfortunately, it was in that sample, but good to know it's in the biofilm. So I looked at the biological, chemical, and physical ecology of the Potomac River to find out what influenced where microplastics ended up. I did take some water readings like temperature, turbidity, so how clear the water was, pH, and some chemical nutrient analysis of the water. But I was primarily looking at the algae and invertebrates in these biofilms and the picture on the left. All of that is just a mix of maybe some sponges, the green patches are green algae, brown algae is in there. There may be some little larvae in there. But again, zooming in, over here in the picture on the right, there is a bright red fiber. So there's microplastics just prevalent in these biofilms as well. And then to give you a better sense of the organisms in these biofilms, these are some of the, this is my favorites, some of the cooler ones. So on the top left, we have a sponge. We probably know what a sea sponge is, but they're in freshwater too. And they're just a colonial group of organisms that pull water in, and they're filter feeders. So that means they pull water in, they take in all the nutrients or food they need from that water, and then expel the rest of the water back out. And that goes for bryozoa too, filter feeders. So in that process, they may be ingesting microplastics if they draw the microplastics in with that gulp of water they're taking. There was some filamentous green algae, as we just saw. This stuff is alive, so it is actively flowing. But as that just flows around on the water surface or in the currents, microplastics can run into that and get tangled up and then deposited into the biofilm. And lastly, we have some tube dwellers. So for this burrow, this brown tube on the right is actually a burrow that a caddisfly larvae made. And lots of different beetles and flies, they start their life cycle in the water. So a caddisfly will turn into a flying insect, but its larvae builds things like this in biofilms. If microplastics are present in the biofilms and they're scraping up a lot of the mud and sediment and maybe some algae to construct their home, microplastics could be constructed in their home as well. So I looked at how the size of these biofilms, how the amount of species in the biofilms affected how many microplastics they would trap inside of that assembly of organisms. And then, as I mentioned, I also looked at different water quality parameters and how those affected where microplastics ended up in the water. So from surface down to a certain depth. As it happened, there weren't many significant interactions. None of these had a big effect on where microplastics ended up. But it's fine, it happens. That is why we do science. So neither the size nor the species composition of these biofilms really affected where microplastics ended up or how many microplastics were taken into that biofilm. But there was still a story to be told there. So again, on the right, we see one of these biofilms. We can see some more of the filamentous green algae, a lot more sediment deposition, a lot more of the brown algae growing. What we found was that when the biofilms were mostly just algae, and this occurred in the winter months because a lot of those invertebrates, the sponges, the bryozoa, fly larvae, they're going dormant or they're just not around in the winter months. It's cold. So we just had algae settling on these surfaces. That, when those biofilms were smaller and mostly just algae, they contained the most amount of microplastics. It also happened that there were the most amount of microplastics just in the water, just existing in the water during the colder months. But looking at statistical proportions, there were still proportionally more microplastics in the biofilms when it was just algae. And that's very interesting because as invertebrates move in, they're having we are seeing a lot more ecosystem services happening. Those filter feeders, those things building, or like constructing burrows in the biofilms. There's a lot of activity in there that may be stirring up the microplastics. Or as things like the amphipods move in, they're grazing, they're having a great time eating those little seagrasses. But if those have microplastics in them too, they may be ingesting the microplastics. My research didn't go so far as to find out why, if those were the reasons that there were less microplastics in the winter, but it still points a very interesting light into the dynamics of these biological and physical conditions. Also, as the water cools and warms, or as there may be more rain, which decreases the amount of salt in the water, these factors also affect the buoyancy of the microplastics and therefore how quickly they settle, how quickly they drop out of the water, or if they just kind of float suspended there. And another closer look. This is again a dried biofilm, but right in the middle, if you can see that small black line, another example of a microplastic just caught up. This one actually looks like it may be attached to a salt crystal, which is very interesting. And back to Elisa for her research.
All right, now we're going to transition into things that are a little more solid. So for my fellowship at the EPA, I focused on microplastics and biosolids. So we'll start off with what are biosolids. So biosolids are also commonly known as sewage sludge. So it's the solids that come out of the wastewater treatment process. So during the wastewater treatment process, all the water's collected, and it starts off with screening. So trash is removed. Anything that floats is screened off as well. And then where biosolids really shine is the settling process. So all of the solids sink to the bottom while the water moves on to more processing. And then the sewage sludge is treated. So we have 3 different classes of biosolids. So we have B, A, and AEQ, and those are categorizations of different pathogen levels. So AEQ is the best for like handling, whereas B it's a little more iffy on the pathogen, like viruses and bacteria. So it's a little more dangerous for humans to interact with. And then there's a dewatering process, which kind of more solidifies the sewage sludge of the biosolids more. And then the biosolids are transported for different purposes. Slide. So where are these biosolids going? So when we transport them, they can be landfilled. So they're just going to be thrown out with the trash. There's also the 1% from 2022 annual reports is deep well injection, storage, not very common. And then biosolids are also incinerated. But then they're mostly land applied. So sewage is great fertilizer. And, there are a lot of people who benefit from the use of biosolids. So that made up 56% of the use of biosolids. So in the year of 2022, 2.12 million dry metric tons of biosolids was generated. And so 31% of that went to agriculture. So it's land applied for fertilizer. Usually that is class B. And then we have 20% of other. So what's other? It's any non-agricultural fertilizer type use. So when I talked about the class AEQ, where it's safe for handling, you can use biosolids in your home garden, landscaping, golf courses use them. So if you don't really want to use biosolids or you're concerned about them, if you go to your Home Depot or Lowe's or wherever you buy dirt, if it's amended with fertilizer, you can usually look at the back and see if it's biosolids or not. So I'm thinking locally, but DC has DC Water. Their biosolids product is called Bloom. So yeah, we interact with biosolids a lot more than we think. We kind of think we just flush away and, you know, it's gone. But biosolids are really important. And well, why is this important? I'll tell you why. So biosolids are a pathway that connects our anthropogenic contaminants to the environment. So when we think of anthropogenic contaminants, obviously we're thinking in the context of microplastics, but there's also perfluorinated substances like PFAS, pharmaceutical waste. So when you ingest pharmaceuticals, your body doesn't use it all, so it comes out in waste. And other contaminants, but anything we wash off our bodies, anything that goes down the drain, toilets, sinks, it's going to biosolids and potentially the environment. Next slide. So when we think about land application, we can look at agricultural soils and kind of analyze the microplastic population that way. So within agricultural soils, 300 to 10,000 microplastics particles per kilogram were found in agricultural soils. That's a huge range. There is a lot of variation, especially in microplastics, concentrations in microplastics data. But 10,000 microplastics per kilogram is a pretty staggering number. So that's, you know, the biosolids are really, so these are agricultural soils with biosolids amended to them. I will add to that. But, you know, biosolids are really concentrating all of the solid waste and everything that sinks down to the bottom in those separation tanks and just kind of compacting it. And then we're putting it on agricultural soil. So with croplands that had biosolids added to them, there were more microplastics found in the runoff. So runoff is when there's a lot of precipitation or rain, and the ground doesn't absorb the rain, especially in croplands. Sometimes we have a little bit of an absorption issue, especially if the soil hasn't been taken care of very well. So then that water just washes right off. And this happens a lot on streets as well, if you want to think of runoff. So, you know, and then if they don't run off, the microplastics also interact with the soil, so they can physically change the soil properties. Microplastics have been shown to move up and down and laterally within the soil column, if you will. And then the microplastics are back out into the environment. So they degrade, and when they degrade, they're multiplying. So that degradation comes with UV exposure, bacteria. There are some bacteria that consume microplastics or that colonize on top of them. And then there's also disturbance of the soil from mechanical tilling or plowing, as well as animal ingestion, animal burrowing. That's a big one. And then, you know, the surface runoff, like I said, moves the microplastics. So yeah, we have this land application on agricultural soil, but then it's not staying there. Next slide. So again, why is this important? You know, we hear, I recently got feedback of like, well, why, you know, your research, yeah, we know microplastics are everywhere. So like, why does it matter that you're finding it in the Anacostia River? Why does it matter that you're finding it here or there? Or, you know, we get new articles every day if we're finding them in placental tissue or in our drinking water. And, you know, it's important because we need to monitor this, you know, even if, you know, in an ideal world, microplastics wouldn't be detrimental to our health, to anyone's health. And, you know, that's that would be great. But, you know, we have to monitor the situation until we can adequately, you know, deal with it. So microplastic concentration data allows us to observe baselines. So even if, you know, my research looked at microplastics, it was the first published paper in the Anacostia River. So we had no microplastic concentration data in sediments of the Anacostia River. So if somebody wants to research the Anacostia River, they have my data to look at, and then they can see, you know, has the situation degraded? Has it improved? And then if there are remediation efforts, then we can see how that has changed. So the concentration data can also help us determine where microplastics are coming from or where they're going, as well as you know, which areas of the country or which areas in our city. Is it industrial areas? Is it urban areas? Is it areas where people are using bloom or, you know, biosolid based fertilizer? And then, you know, water's running off from their gardens into this local waterway. So those are things, you know, we really have to take into consideration, especially the movement and, you know, what's happening to these microplastics. And so all of that helps us calculate risk. So we're going to put our human health risk assessment hats on. Some people don't find this interesting. It is, we'll go into it. It's important. It's really important. So how do we determine if something is risky? And this can be in our everyday lives. So, you know, every single day we make 1,000 decisions as to our behavior, what we consume, what we wear, what kind of chemicals we interact with. So like, how do we determine if that's risky? And a lot of the time, our brain is making these micro decisions. However, in the case of human health risk assessment, it's a lot more complicated than that. So then how do we know if something is bad for us? So I like to think of I put the picture of the dog jumping over the fence because, you know, risk is subjective. Risk, something that's risky for me may be different, may not be risky for someone else. So if I want to jump a fence, maybe 10 years ago, my risk would be very low. But if Joe broke his arm and he wanted, you know, we were like, hey, come jump the fence, we're going. His risk of jumping that fence would be different. His outcome, his risk is higher, maybe, perhaps. So when we think of risk in terms of maybe ice cream, you know, the dose really makes the poison, too much of a good thing, if you will. Or in the case of human health risk assessment, the exposure makes the poison. Next slide. So when we think of exposure, we're really thinking of our 3 main exposure pathways for human health risk assessment. So that is ingestion, so when you eat it, when you drink it; inhalation, so there are microplastics in the air, or, you know, I like to crochet, and I was making a hat for my friend's dog, and I made a pom-pom, and I was trimming, making really fine trimmings of this acrylic or plastic-based yarn, and I found some in my nose the next day. So I was like, I inhaled some microplastics. That was self-inflicted, but I mean, that is a high risk. That may be a high risk activity. And then there's dermal exposure. So like if something touches our skin, how does our skin react? So, you know, we have a lot of plastic-based clothing, synthetic fiber clothing that we come into contact with almost every day. Other exposure pathways can be through sea spray, so you can breathe in sea spray, it touches your skin. The chemicals from the plastic can come out of food packaging. If you have, you know, styrofoam, and you're not supposed to microwave it with food in it, there's, you know, you don't want to heat it because then that can maybe cause some chemicals to come out onto your food, and then you're ingesting it. And then we have the issue of really, really tiny microplastics or nanoplastics. And those have been found to be able to cross cell membranes. So, we don't really know how they interact with our cells. So, you can encounter nanoplastics in any of those three exposure pathways. And then recently there was a huge study about microplastics in our drinking water, and that previous studies have overly underestimated the amount of microplastics in our drinking water. And then our food. So our food comes into contact with packaging, as well as there are studies looking into how plants interact. So we were talking about agriculture. Do plants take those microplastics in their roots? Does it travel to the leaves that we eat? If we eat spinach, does it, how does our food system interact with microplastics? Next slide. So there are 4 basic steps to the risk assessment process, and I'll try to frame this in the context of microplastics. So first we have hazard identification. So that's how we determine whether the exposure to microplastics can cause adverse health effects in a higher rate than if we weren't exposed to them. So this can be cancer, birth defects, diseases, tumors, reproductive issues, as well as death. So it's also whether or not the adverse health effects can occur in humans. And then we have our dose response or dose concentration response. So this relationship shows the likelihood of adverse health effects related to the amount that we're exposed to. So like the ice cream, if we have, if we eat more, maybe our health, decreases a little bit. And so usually what happens with the dose response is there's research that goes into it where they expose usually animal subjects to different levels of a contaminant, and then they record at which levels do they see health effects. And then we have our exposure assessment. So this is how the process of measuring or estimating the magnitude, the frequency, and duration of human exposure to microplastics in the environment. So it includes a discussion of size, the nature or types of human populations that are exposed to microplastics. So, microplastics are everywhere. So a human health assessment could be population-based, or it could focus on certain communities or certain subsets of the population that are more at risk or that are more exposed. And the exposure assessment really compiles all of this data, and all of this data goes into models, so mathematical models that we put in the data, and then we predict, we predict how this will affect us. So the chemical transport, how microplastics move, where they end up, what they do when they end up there, estimates of human intake over time. All of that goes into a model. Then that kind of spits it out into an exposure assessment. So data is so important, especially in terms of a model, because you can either overestimate it or underestimate it, and there are a lot of uncertainties. So you want to make sure that you're ready to conduct that. And then that all kind of culminates into risk characterization. So whoever's in charge of the risk assessment kind of compiles all of this data, and then they make the judgment of the nature and the presence or absence of the risk. That was a marathon. All right. So now that I've kind of, taken you through risk assessment, we'll get into the specifics of microplastic risk assessment. So currently, there isn't one. And that's because there are so many unknowns when it comes to microplastics. So microplastics research is 20 years old. In the scientific community, that's that's a fetus. Like that's very, very young. And we've made leaps and bounds. But with those human health risk assessment process, kind of frames what kind of things do we need to know about microplastics. So like, how do we address the diversity? So most chemicals or suites of chemicals or chemical classes, they can all be treated the same. However, microplastics are so diverse. Can we all just say this is microplastic? Or is it polyethylene microplastics, polystyrene microplastics? So where do we draw the line, and how do we define them to be able to address those problems? And then so we can know how we're exposed, but just not how much. So we have all of these pathways of exposure, and there may be even more that we don't know of, but we just really, there's not enough information right now of how much we're exposed to. There are new studies being published every single day. And then, with risk assessment, we find out how much is too much. With that dose response or concentration response, that's how we determine how much is too much. And then we can go into how does this affect children or adults, or who's most vulnerable. So usually risk assessments deal with children and adults separately, because different doses affect smaller humans versus larger humans. And, sometimes children, or a lot of the times children, are more vulnerable, especially with developmental impairment is a big one. And then with monitoring microplastics, right now, we don't have a standard method to find them, to analyze them, to classify them. So that's a huge impediment to kind of standardizing concentrations and being able to cross compare. And that is it's coming closer to that every single day. So I say, oh, we have all these unknowns, but there's good news. Research is catching up. So a paper was recently published about estimating the mass. So usually when we calculate microplastic concentrations, we look at the number of the particles. But if the monitoring method has estimated the mass, the total mass of a microplastics in a sample, that's a huge step towards human health risk assessment, especially because human health risk assessment, if we're analyzing a different chemical, let's say like DDT, or if we're ingesting DDT, we would know the amount or the volume or the mass of that chemical versus, a number of particles that are, can be that size, this color, made up of this chemical. That is much more difficult to be able to apply to a dose assessment.
Yeah, thank you so much, Elisa. That's lots of background information, lots of great information. And I'm going to take the next few minutes to maybe bring the mood up a little bit, at least try to. And I'm going to talk about some current policies, some proposed policies, and just ways that individuals and society can address all of these issues. So when we talk about plastic waste, just a little bit more background information. The United States has produced 20% of all the global plastic production, all the plastic in the world. And that is a lot for especially just one country. And as Elisa said, microplastics, that word was coined in 2004. So this branch of study has only been around for 20 years, 20 years as of 10 days ago. So yes, in the science community, that is brand new. So it's incredible as to how much we already know, but also how much it's important. Like, it's good that we know how much we don't know too, because the gaps are where we need to focus. In the United States, I'd say that we can pinpoint the movement to reduce plastics and to address microplastics to a study from 2012. And this was the first study that found microplastics in the Great Lakes. The Great Lakes are a shared resource between Canada and the United States, but also the largest source of fresh water, accounting for, I think, 80% of all freshwater in North America, maybe North and South America, but it's a huge body of fresh water. This study differentiated this pollution from coal ash. So it distinctly said these are microplastics. These are not just run-of-the-mill, in quotes, run-of-the-mill pollutants that we find in this water. These are microplastics. And they were able to look at the industries in the area and realize that a lot of those microplastics came from cosmetics. And so there was a large movement for between state, municipal, and leading up to national legislation to counteract those microplastics. But as we start to look at more political frameworks to address microplastics, and the plastic crisis in general, we can draw on other sources at different levels, municipal, state, federal, international, and create a framework to guide economic, environmental, and public health aspects. We unfortunately don't have enough time for this interaction, but I'll keep going. So one key way that policies can address plastics is to start at the source. If you simply don't have plastic, you simply won't have microplastics. So we can look at some bans that have been pretty effective. And leading off of that 2012 study from the Great Lakes, we got the Microbead Free Waters Act in 2015. This banned microbeads. Microbeads are still microplastics, just small little spheres. This banned microbeads in cosmetic products, so anything like face washes, exfoliants, all of like that grain that used to be in those products were microplastics. And that's how you exfoliated. So this banned those in those products. And now we have like, I've looked at the ingredients on my exfoliant, my face wash, and it was like walnut shells. So I think that's a little more sustainable. Maybe don't eat it if you have a nut allergy. That's probably for the best. But if we look more broadly, there's also sweeping movements like in the European Union that banned a lot of single-use plastics. And this is on the right, that cover page of their decision to ban many single-use plastics. But again, there's so many different types. So some acts have to address things like plasticizers, such as the United States 2010 Bisphenol A Free Children Babies Act, and that banned BPA in children's toys. So bans are good to just prevent plastics from being there in the first place, maybe plastics that aren't needed in the first place. But what do we do with the plastic that's already out there? In this case, we need to look to mitigate the damages of plastics that's already in existence. And we see this being addressed through bottle bills, such as New York and Connecticut. Connecticut actually just recently updated their bottle bill, and the bottle bill is that redemption scheme where you bring your bottles and cans to the grocery store or to a redemption center, and you get 5 or 10 cents back. In Connecticut's used to just be kind of like soda bottles, soda cans, but this update from 2021 expanded that into tea containers and water bottles, I believe. So a much broader array of plastic items that you can get 10 cents for back. This does involve corporate involvement, and when we try to make these laws, there's a lot of corporate pushback. And the way that these bills work is you initially pay up front that 5 or 10 cent fee, I believe. Terry, I think, can correct me at the end if I'm wrong about this, but the consumer pays that up front. When you return those, you get that deposit back as a refund. The grocery store reimburses you, but the companies, the corporations that produce that plastic, then have to reimburse the grocery store. Obviously, we live in a very profit-driven society, so companies don't want to do that. But these are some of the sweeping legislations that need to occur to address the plastics at such a broad scale. And again, we talk about broad scales, we want to talk about the infrastructure. So for example, the wastewater treatment plants where we get the biosolids from. Elisa talked about that direct pipeline of microplastics down the drain into wastewater treatment plants and being not captured in that treatment plant. So one way that we can try to capture those plastics up front is, one example, California had in this past legislative session in that state, Assembly Bill 1628. This would have mandated a microfiber catchment device on laundry washing machines. So you would just have to take that out every once in a while, scrape off those fibers and throw them away. That is a direct solution to not let those plastics end up in the waterways. That bill, unfortunately, was vetoed. I don't know why. I don't live in California. Have not heard all the news, but I do know that bill is back in the General Assembly, and they're trying to see if they want to overturn that veto. So stay tuned on CAAB 1628. I talked about the wastewater treatment plants, but also combined sewer overflows are very popular, not popular, but very widespread. I wouldn't say anyone really likes them. They're widespread here in DC, and I know in Connecticut we have combined sewer overflows, and that's just a connection between the sewer and the stormwater drains on the side of the roads. All the piping underneath that is connected. So if we get a heavy rain event and the drainage, this rain drainage overflows, it'll overflow into the sewer pipes, and that will just cause mixing. So wherever that rainwater is supposed to go into an underground aquifer or a river, we're gonna get sewage. And as we saw, there are microplastics in that. So if our municipalities, our states, our countries can get on board with infrastructure overhauls or just updates, that would go a long way to addressing microplastics as well. And all of this leads into a circular economy. So our current system is take, make, waste. It's just taking, extracting from the environment, making it into a product, and then once it's used, we typically just throw it away. It ends up in a landfill, out of sight, out of mind. But a circular economy, these types of practices are much more based on the reduce, reuse, recycle schema that we're aware of. There are many ways we can add a fourth R into that. My favorite is simply refuse. But I was just reading an article about half an hour before I jumped on here. Philadelphia, there's a nonprofit in Philadelphia, Pennsylvania, that is giving $600 to businesses, to restaurants in the area, to pay for either staff training or different types of washing machines, just reusable products to decrease the amount of plastic that they're using. That's a perfect example of refusing the single use in the first place. They called it rethink. So many different fourth R's we can add on to reduce, reuse, recycle. Other systems are sort of plastics credit systems, and these are similar to a carbon cap and trade, where companies can pay other companies who are doing the work to reduce plastics to kind of allocate their own plastic usage. And these definitely have issues. Absolutely, they do. But it's still a step in the right direction. These systems will need third-party verifications. Just as technology expands and updates, we want to make sure that everything is still kept in line with the original proposed documentation. And then extended producer responsibility. This is a concept that just requires the producers of plastic products to account for their end-of-life cycle. And that may come in the form of financial costs. In environmental economics, there's going to be some sort of damage to the environment from creating or using this product, and that's called an externality. So in this case, we may want to internalize the externality and make those products more expensive, and that will disincentivize the usage or creation of those products. There's also some legislation that can be done. Washington State has a fine on styrofoam takeout containers. So if they're used, that business has to pay for them. In a lot of places, I don't know where it's been reinstated since the pandemic, but in a lot of places, there was just a 5 or 10-cent fee on plastic grocery bags. Those are amazing ways to just disincentivize the use and, again, refuse using plastic in the first place. Or in other court cases, DuPont, for example, had to pay $5 billion for Teflon damages. If anyone's seen the movie Dark Waters or the documentary based off the same concept about DuPont and all the Teflon damages, definitely recommend that movie. But as these things start happening, there's going to be like education campaigns and mass movements, mobilizations as people learn more about plastics. So it's very important, first of all, you came tonight. Thank you again so much. But the overarching concept here when we talk about policies is that there's going to be, first, many policy documents over time because of the nuance of this issue. We need to turn the public awareness into the new normal. So small habits that we can make in our community or in our own homes is going to go a long way. When you just talk, when people see these actions and mimic it or just learn about it, it becomes habit. The biggest thing that we need to take away is that there's involvement on all sides. So individual action is outstanding. Keep doing that. Keep doing your best. But we also need to involve governments at all levels and the corporations, whether that be through disincentivizing or getting everyone on board for things like removing useless microbeads from exfoliants. So there's this overarching concept of a system change rather than individual change. And that comes with balancing the economic, environmental, and behavioral participation at all levels. Again, individual, municipal, state, federal, and corporate. So the takeaway for like your action after this is to just get involved, talk about talk about the many problems of microplastics. And these 9 issues in the bottom are a summary of what we talked about. So we can prevent plastics in the first place, mitigate what's already there, and turn what's already there into a useful product through a circular economy. Incentivize the use of or transition to a circular economy by changing consumption habits, by changing our infrastructure, by increasing our education and doing education campaigns. Really defining what it means to be a plastic, defining what it means to be a toxic plastic, and then looking at plastic alternatives, whether that be reusable or actually, yeah, pretty much just reusable. Like, do we need the plastic in the first place? So with that, thank you all for coming. We'll get to the Q&A. One last picture of a glorious biofilm over there on the right. Just plug for myself, I talk about plastics nonstop on my Instagram, my science communication Instagram page, and Vijo Mental Scientist. You can also look up the next How to Protect the Ocean podcast episode this coming Monday. I'll be talking about the same things again. And again, a huge shout out to IREJN. If you are unfamiliar with the organization, give them a follow, become a member, sign up for their mailing list. They do awesome work. But for now, I will stop sharing my screen, turn it back over to Terry, and we can do some Q&A. I see the Q&A box.
Oh my gosh, this is like the most active Q&A chat that I've ever seen. And so I want to actually just address one thing. There were a lot of comments about artificial turf, and I want to let you know that we are actually working. And I believe the other organizer, I saw her in here. Yeah, she's attending. Susan, we're working to plan a webinar on artificial turf. It's looking like early February. So we'll get that information out to everyone because, yeah, that's a big source of a lot of different issues. However, let's just jump right into it. And it's amazing that we did another webinar with the Harvard Society of Friends. We co-sponsored on the story of plastic and had another wonderful speaker. And it's amazing how diverse this topic is, that we did a presentation in October on plastic, and we do a presentation in January on microplastics. And I mean, the information is completely different. It's just such a huge topic. Let's see here. Can you talk a little bit about artificial turf? There were several questions in the chat, and like I said, we are doing a webinar in February. But can you talk a little bit about artificial turf and the impact it has on microplastics in our environment?
Yeah, I can start real quick. This is definitely an area that I need to do more research on for artificial turf specifically, but it is plastic. And if you ban artificial turf, you have the fake grass, but under that is just a layer of essentially nurdles, just those little black plastic pellets. Those are obviously going to get brushed off with rainwater. So it's not that absorbent. Rainwater is going to flow off of it in high rain events and carry some plastics with it. Just normal wear and tear is going to kind of tear up that the fake green grass, and so that's going to become a microplastic. And it's a direct pathway into, I mean, you're probably tearing up an already existent turf field to put plastic in, so it's already in the environment. But this is a direct pathway into watersheds and other interconnected parts of the environment.
Shawnee was wondering, actually, on the same vein, do you have any tips for speaking to local boards who seem to be hell-bent on installing artificial turf in spite of in spite of the environmental reports that we give them?
Yeah, in my experience, talking with legislators, yeah, it's all about the money. And if you can be like, this is too expensive, maybe the environmental benefits are not going to outweigh whatever they're used for. I guess like joints. I don't know. What are artificial turf fields beneficial for? Like
Maintenance, probably cutting
maintenance.
off.
Yeah.
Yeah, exactly. That's what they say. I mean, but in reality, it's like
There's
so
a
it's so
cost
devastating to
benefit
the environment. You've got
analysis for sure that
kids playing on stuff that's like magnitude more hot, and on a hot summer day, and yeah, no, they're a mess. So I will say, actually, we will have an expert on artificial turfs at our webinar in February. So some of these artificial turf questions I'm going to automatically sort of put onto that one, so that we because I know we're going to have someone who can answer all those questions really easily. So Paul actually wanted to know, are you aware of any legal action being taken against the plastics industry to drive or force changes in their product creation and liabilities for harm?
Kind of a side answer to that. I know of two federal bills that are going around right now. One is specifically about styrofoam. I don't remember the names of these right now, but one about styrofoam, and then one is just sweeping plastics legislation, plastics bill. Um, I imagine there's going to be lots of pushback from the plastics industry. I guess I can only think of more broad climate legisl or court cases, things like what is it, Juliana versus the government, like the youth movement to against the government's inaction on
The
climate change.
right to a healthy environment, right? Or
Yeah,
healthy
yeah.
environment.
Thanks. I personally don't know of any
I don't know
against plastics.
of any lawsuits either.
I know of
I
several cases where the plastics industry steps in to lobby for or against certain bills. Elisa, what were you saying?
I think about that in terms of I kind of equate when I think about that question, I also think about like the fossil fuel industry and holding those industries accountable and how hard that is and how much money is at stake and there's so much politics in it. Um, so yeah, that's what my first thought was, not no, but hopefully that's a not yet.
Well,
Right,
and
it's not
you
yet.
actually, that was a great segue into comments about the fossil fuel industry. Someone had a question about what are the impacts of the emissions from burning plastics in the trash burning facilities. And then I saw something else in the chat talking about the dangers of the sort of false solution of advanced chemical recycling, which is just burning plastic.
Yes.
So can you connect the dots between the fossil fuel industry and the plastic industry?
Yes. So before I started grad school, I lived in Galveston, Texas. I was an aquarium biologist, and my first culture shock, Galveston. If you're not well versed in Texas geography, is right adjacent to Texas City, where there's a lot of oil refineries. So Texas is a big oil state, and I remember one of the first days I moved to Texas. The governor said that plastic is good for the environment. So that's, petroleum-based products are used to manufacture plastic. So, when we burn them, because plastics are carbon-based, they are creating hydrocarbons, just like any other carbon-based and petroleum-based product would.
And what I've learned is that the fossil fuel industry is moving more to plastic because they know that the renewable energy and energy efficiency is really taking over. They don't see their future necessarily in the energy generation here, at least in the States, but they're pushing the creation of single-use plastics and then also the creation of advanced chemical recycling facilities where they can burn the plastic because it burns well because it's basically oil-based.
That's exactly what I was going to say, that the plastics industry is keeping the fossil fuel industry alive. And I think it's projected to grow. Plastic is actually the largest or like fastest growing industry. It outpaces steel now from the Industrial Revolution. It's that widespread. And you can look at the graph of, this is definitely correlation, not causation, but you can look at the graphs of plastic production and greenhouse gas emissions and the warming temperatures, and they follow the exact same pattern. Because yes, plastic production and plastic in the fossil fuel industry directly tied, and plastic production and climate change is directly tied as well, because it's all petroleum based. It's all oil and gas, mining, refining, manufacturing. Terry, going off of that though, wasn't Mira in Hartford closed?
Yes, it was. And that's actually a big part of the discussion is what is that area, what is that space going to be used for? And how are we going to handle waste in Connecticut? And specifically, there's going to be a big food waste, hopefully a food waste bill that will be really, really critical, that we'll talk about composting and that sort of thing. Someone actually had a question in there that asked, if we're using biosolids in our agricultural source, are the vegetables and the fruits absorbing the microplastics into their into the veggies and fruits?
That's
I
a
think the
huge
answer is yes. I
point
think
of research. Yeah. Yeah. And, a lot of it is in the roots. And then, in terms of like super, super small microplastics, we don't know yet. So, detection methods for finding microplastics, especially super, super small ones, are still emerging and they're still being refined. So there are microplastics that, a lot of research hasn't accounted for because we can't find them yet.
Mhm.
Oh, and I was going to add, if I can, another reason why any court cases would be so difficult is because microplastic or plastic science is so new. So 20 years is not a long enough time for a human health study, because humans generally live a lot longer than 20 years. And so you could bring some scientific papers and documents to court and say this is projected, or like we have microplastics in our body, but there's no real, I guess, court evidence to support human health detriments because of plastic on a large enough scale that you could take them to court, I suppose.
Mhm.
I like to compare microplastics to PFAS because, 20 years ago, PFAS was in the same, area of microplastics. So, people kind of like knew they were there. They knew they might be bad, but, now 20 years later, you have, community testimonials of people dying of cancer. And now there's this immediacy to, address the problem. So, hopefully microplastics will move, we've learned our lesson, and to not, ignore something that's so ubiquitous and so pervasive. So hopefully we won't wait as long to kind of, progress the science and find out.
Nancy has a really good question. She said, I read an article today that connects the presence of phthalates, the substances to make plastic more durable, in a study between those hormone disruptors and early onset puberty in young girls. Have you read anything about microplastics and endocrine systems?
I'll tackle that one.
Yeah, go for it.
Yeah, so usually, with microplastic studies and endocrine studies, usually there's no correlation with the direct impact of microplastics, but usually it's the associated phthalates and other endocrine disrupting compounds that are added to plastic. So that can be like pituitary issue or thyroid issues. I looked at a study that looked at phthalates in like medical tubing, which is a big problem because you have like babies in the NICU who need medical tubing. So plastic is so pervasive, but there are also needs that plastic addresses, especially in like hospital settings and keeping things sterile. but we don't need phthalates in medical tubing. But finding an alternative to keep people safe is definitely important.
And on the topic of safety, Pippa wanted to know, are certified organic foods safe to eat?
Yes, most likely. I think there's, in terms of microplastics, I guess we don't totally know that because, Elisa, could you apply biosolids and still call it organic?
Well, no, actually, so I should have read the whole comment, I guess. She said,
Oh,
I
okay.
found this on the internet. Note that under the United States Department of Agriculture's National Organic Program, biosolids and compost produced from biosolids are prohibited for use in organic agriculture.
There we go.
So in biosolids as of last year, of the contaminants or chemicals that we are able to identify, there are millions and billions of chemicals. We only know the structure and what a select relatively few chemicals are, but more than 600 chemicals were found in biosolids samples. So that can include pharmaceuticals, PFAS, like pesticides for sure, if it's washing off of people's if they're wearing bug spray, if they're taking, if somebody has like medication for worms, or like any any insecticide, that couldn't, that those biosolids that come from that couldn't be organic. So there's no way for us to control for that in biosolids, so they're not counted as organic additives.
Lisa, can I get your opinion on the use of biosolids? Because I would think it's still a sustainable option. It's just more the infrastructure that allows those chemicals and microplastics to get into it.
Right. So, recycling is great. My personal opinion is right now, I wouldn't choose to use biosolids on like if I were growing a home garden, I would not choose to use them knowing what I know. But I also I know how many chemicals are in them, but I don't really, know what they do or how they affect me. But it's such a nuanced issue, because then what do we do with them? I know Maine had a huge PFAS issue with biosolids. So there was like an organic spinach farm, or it was like a co-op, and they had to close down because their produce had really, really high levels of PFAS. And even the farmers had like double the amount of PFAS in their blood than the general population. So Maine is a huge, they don't land apply biosolids right now. So there is a lot of research in emerging technologies to treat biosolids. But in terms of microplastics, we don't really have the infrastructure to address them. And then it's even harder, even within our water treatment systems. But then within biosolids, it's such a complex matrix. It's fatty, it's sticky, you have all of these, it's just a complex matrix, and it's really hard to study, but it's really hard to treat as well. So there's a lot of research going into how to do that, especially for PFAS.
Thank you. I have two water related questions. One is, what is the best water filter to remove microplastics, if any? And then Marge asked, did you see the CNN report about nanoplastics in bottled water? Can we ban bottled water? Yeah, I mean, so basically, Marge, I did see that report. It was horrifying about how much microplastics is in bottled water. What are the options around bottled water, and is there a water filter that can remove it from your tap water?
Do you know the answer to that one?
So when I taught the environmental science lab at American University, we did a microplastics module, and a lot of my students chose to compare bottled water versus tap water versus running water through a Brita filter. and they didn't find any significant differences. So, you know, a lot of our filters aren't really designed to address plastics. However, the closest one that I can think of that is the most effective is a reverse osmosis filtration system. However, that's like installed in your home level. Like
Right.
it's, yeah.
That is not
Um,
acceptable for most. But are
right.
you saying that there was no appreciable difference between bottled water and tap water? The tap water had
A
as
lot of
much.
the times bottled water is just bottled tap water.
Oh,
Yeah.
but they're not more microplastics leaching into the water because it's in a plastic bottle?
I wouldn't think it's a significant difference because, you know, when I think of like the plastic bottles, they're pressurized. So, you know, you don't really, unless you're like shaking the water bottle and like really like crunching it up and then drinking the water after, there's not a lot of at least mechanical um, agitation to create those microplastics. So
Interesting.
the
I know
source of the
that
microplastics in the bottles would most likely be from where they're manufactured. So if there's contamination from, you know, the factory and like filling them, if there's like chips of plastic of the bottles, you know, that way, or just from the water source.
Mhm.
And then for the water bottle question, yeah, at least they were pressurized. But yes, there are still plastics in them. And going to that CNN article, that if it's the one I'm thinking of, they found 10 to 100 times more microplastics than previously found or previously thought in water bottles. And part of that definitely comes from the water bottle. Maybe not to the extent like that we think, as Elisa said, but and I think the second part of the question was, can we ban water bottles? And in my personal opinion, I think just don't people need to not use them if they don't need them, because there's still a mechanism to deliver clean water to places that don't have clean water. Um, where was it? Oh yeah. And then like, yeah, as Lisa said, bottled water is mostly just bottled tap water, or in horrible cases, just stolen water from indigenous lands they bottle up and sell back to the people and back to the population. So I think it's still a valuable way to have a source of clean water. It just does not need to be as widespread as it is.
Thank you. Yeah, and actually someone just corrected me. The report today was about nanoplastics, not microplastics. So maybe I'm thinking about a different report. But let me see if there are more more questions in here.
Yeah, nanoplastics are even smaller than microplastics, because as we said earlier, microplastics are like just 0 to 5 millimeters. Nanoplastics are like those are the things that can pass into your cell membrane. They are very, even just unfathomable scale as to how small they are.
Bobby actually wanted to know who was governor in Texas when they said plastic was good for the environment. It can't possibly, I mean, Bobby wondered if it's W, but I'm like, there's, Elisa, you're not old
That
enough
was in
to have
2016.
been aware of who the governor was when he was governor.
I was not very politically active in Texas when I lived there.
Was it, do you remember who it was?
I don't remember who it was.
Oh, okay. It couldn't have been W.
It was in 2016.
Yeah, you're way too young. Okay. All right. So actually someone was saying, is it dangerous to wash plastic bags out and reuse them? Um, sometimes you get those like Ziploc bags and you're like, oh, I don't want to just throw this out, use it again. You wash it, you let it dry. Are you releasing tons of microplastics, or is it like, well, at least you're not putting it in the trash,
I hesitate to say dangerous, because I mean I just talked about all this risk, but like rinsing out plastic bags and reusing them seems like incidental microplastic
Mhm.
formation versus other mechanisms to create microplastics or to just throw the plastic away. Because they are so ubiquitous. So,
Right.
you know,
When I talk about Yeah, when I talk about plastics, I always use this little story about walking into the store to look for a birthday card and realizing that every single card that already had a little paper envelope was also encased in a plastic envelope. So the
Mm.
envelope needed an envelope, you know, and that's really, and the more you look around, the more you see single-use plastic being used for things that it definitely doesn't need and hasn't needed before. And that's really where policy is needed to stop the sort of shenanigans. From, again, that's just the fossil fuel industry trying to convince everyone that if it doesn't come wrapped in plastic, somehow it's not suitable for sale, you
Not
know?
clean, it's not,
Yeah,
yeah.
exactly. Let me go back. Okay, we're at 8:30. Let me see if I can get any more. Uh, ooh, someone wanted to know, has anything been done to get the manufacturers of kids' toys to minimize or stop using so much plastic um, for toys? The pack for plastic packaging for toys.
I think that would fall under one of the current federal bills that wants to tackle single-use plastic broadly. I'm not sure of any actions that are targeting, again, like producers directly. It's going to be more
Mhm.
large scale, all-encompassing action. Lisa, do you know of any?
I don't. Not specifically for children's
Hmm.
packaging.
And so I just so this is the last question. It's 8:31. I don't want to keep anyone too late, but Tom asked, is there anything we can do to counteract the massive uh, build out of her plastic production facilities? Is that, I mean, that just sounds like local grassroots organizing to me, you know?
Yes, I was trying to think of a way to say that, but essentially, yeah, I think it's all about like putting enough pressure, putting enough societal pressure and societal normativity on combating plastics. And unfortunately, it's not going to happen overnight, but like it's definitely starting. So just we gotta, yeah, keep the pressure on, um, keep the science coming, keep those articles like CNN articles coming. It's all really good work, and it's going to lead somewhere.
I am going to share this last um, well, hopefully you can see I apologize. My PowerPoint's really not cooperating with me, but there are a couple different events coming up. As I mentioned, we are going to be putting on artificial turf webinar in early February. But before that, there are even other ones. Clean Cars and Clean Trucks for Connecticut. Sierra Club is hosting a lunch and do on Thursday, January 18th at 12. It's virtual it's Connecticut, but it's an update and action on the clean cars and clean trucks. The Connecticut League of Conservation Voters is holding their environmental summit on Tuesday, January 23rd from 9:30 a.m. to 3:30 p.m. at the Connecticut Science Center. And then on February 2nd, on Friday at noon, there will be a Keep Connecticut's Climate Promise March in Hartford. And so I will, when I send out my follow-up email, I will send everyone the details and how to register or RSVP for these events. We obviously are going to continue our advocacy and our education efforts, so I will keep everyone apprised of that. But other than that, I just want to say thank you so much to Joe and Elisa. This was a very in-depth and informative presentation. We're really, really grateful for your enthusiasm and your willingness to come and talk to us about this really, really important topic. So I think I speak for everyone when I say thank you so much. Keep doing the great work that you're doing in DC. We're glad you are there. I hope that you can, pop in and join us for upcoming presentations, or if you're in the area, come by and say hello, because we'll be working on all these issues.
Yeah, thank you so much, Terry. Thanks everyone for coming.
Absolutely. And just so you know, guys, there's lots of thank yous and blah 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 in the in the question and answer in the
Thank you. Yeah, I was trying to respond to something in the chat. Real quick, Peter was talking about seaweed and mushrooms as biodegradable packaging materials. And we intentionally stayed away from bioplastics, at least tonight, because that is that can be its own presentation. But I think in these cases, these are not constructed as plastics. They are just kind of like groups, just clumps of mushrooms. The seaweed's a little different. Those are bioplastics. At least, do you know anything else about that? What are we going to say?
Oh, yeah, I was just thinking of in terms of like compressed seaweed and mushrooms versus like bioplastics.
Right.
But yeah, like in terms of like the chemical composition, the plastic is even no matter the source, it it has the same backbone. But the source plays a huge part into climate change and environmental issues, though. So
Right.
All right.
All right,
Thank you
everyone.
again.
Thank you so much.
I'll make a stop
That was,
by.
that's really great. Your energy is awesome. Thank you so much, everyone, and have a great night.
You too. Good night.
Bye. Thank you.